one weird thing about the black hole is your listeners may be familiar with the idea of falling into a black hole and getting spaghettified.
Stretched.
The technical term, spaghettification. And the reason for that is if you have a black hole, if you turned the sun into a black hole, if you squeeze it down, so you had a black hole the mass of the sun, it ends up being about a mile across. And the gravity is super strong at the edge of the black hole. You squeeze all the sun down into a million mile across star down into a mile across. But more importantly, the gravity is changing really rapidly. It's dropping off really fast. And so as you fall towards the black hole, say you're falling feet first, pretty soon, well before you get to the black hole, your feet are traveling 1,000 miles an hour faster than your head, which will not be good for you.
We're back for another episode of the Cold Star Project. Our topic is space astrophysics. I'm excited to have Jonathan McDowell here, who's a referral. I was told to come get you, Jonathan. And you are a PhD. You are, I'm going to list a few things here for the other screen, astrophysicist at the Harvard-Smithsonian Center for Astrophysics. Since 1989, you've been the author and editor of your own website, Jonathan's Space Report, hosted on Jonathan's Space page. I mean, the internet was a little different animal back then, right?
On a website back then.
And I mean, folks, this is significant enough to warrant its own Wikipedia article, so it's kind of a big deal. You have a main belt asteroid named after you, number 4589 McDowell, named after you in '93. And another thing that I found out while I was researching is you've been a contributor, or were a contributor to Sky and Telescope magazine from 1993 to 2010. So when you get into something, you really commit to it. So it is Christmas Eve day. I appreciate you picking this time and showing up, because last week, for example, I had 3 out of my 4 guests go, can't make it. So this has been a much better week for recording. So thanks for being here.
Try and show up, yeah.
All right. Okay. Well, Dr. McDowell, let's begin with the Chandra X-ray Center. This is the Chandra spacecraft. Is something that doesn't get as much media attention as the Hubble Telescope, you know. And I went to the website and checked it out. There's a lot of beautiful images there. If people want to, I'll put that in the notes, a link to it. It's been in orbit for 20 years. It's at an orbit ridiculously high up compared to the satellites we're used to, like 86,500 miles, right, flying around up there. It just, for comparison, the ISS orbit's at 260 miles. So, folks, this thing is way up there, and the reason for that is the Earth is busy absorbing X-rays, and we want to capture those. So, tell us about the Chandra spacecraft and your involvement with it. How has it been, you know, after performing for 20 years, how's it doing?
Well, it's doing great. And, you know, we're actually hoping, it was a 5-year mission, right? All good Star Treks last 5 years, and the really good ones get renewed. So we've been just super happy with the performance of the spacecraft, and we're hoping for another 10 years. And so, you know, it's showing its age. I mean, 20 years in spacecraft years is you know, sort of like dog years, right? They don't normally last this long. So, so like all of us who started off the mission young and sprightly, it's starting to creak a little, and we have some issues with thermal insulation, where some bits are getting too hot, some bits are getting too cold. The nice shiny, if you see pictures of Chandra, you'll see it has this nice silvery shiny insulation that now is probably like brown and cracked. And there's some gunk that's building up on the main camera. There's probably only a few atoms thick, but it's enough to reduce our sensitivity in some X-ray colors, but not in others. And so we're doing great science. There's a lot of demand. Astronomers around the world use the spacecraft, and my job is to help those astronomers make sure they have the software they need to do the data analysis.
Okay. What if you had the ability to upgrade Chandra right now and put a new version of it into orbit, or go up there and pop some components out and put them in? What do you believe would happen? Would there be any advantages?
Yeah, well, funnily enough, we have been thinking about this. Not so much for going out and repairing Chandra, because that's in the high orbit it's in.
Very expensive.
Easy. I mean, in 10 years from now, maybe you could do that with Orion, blah blah. But so instead, we're looking at the next mission, which we're calling Lynx. X for, like, you know, have an X in it, and it's sharp-eyed, and so the main difference with Lynx would be that Chandra has the thing that was special about Chandra was that compared to earlier X-ray telescopes, it had much sharper vision. So why do you need, let me just, rewind a minute and go, why on earth would you need an X-ray telescope? Isn't Hubble good enough for everything, right? And no, because we see things that Hubble can't see. And but in particular, whenever things go badly wrong in the universe, you get matter at 1 million degrees because you have a supernova explosion. You have very hot matter because it's falling into a black hole and being torn apart. Then the thing becomes entirely transparent to human eyes, but glows really brightly in X-rays. And so you'll completely miss these things if you just have a visible light telescope. So you need the X-ray telescope to see the really cool, weird stuff. It's like, only 10% of the stuff, but it's the interesting stuff, right? And so we had X-ray telescopes before, but their eyesight was pretty blurry. Okay. And so Chandra is so much better, but it's only really, really good right in the middle of its field of view. And the vision gets a little blurry toward the outside, and that makes it less efficient at looking at large areas of sky. So what we want is something that's as sharp-eyed as Chandra, but over a wider field of view and with better color resolution. So roughly speaking, we talk about spectral resolution. So every time we take a picture with Chandra, we get a spectrum in every pixel. That's to say we have many colors that we're measuring at once. And that's critical for understanding the physics of what's going on in these distant objects. And so we have maybe 200 colors right now. That's probably an overestimate. In the normal pictures, we have 10 colors, and we want to go to millions of colors. And so that'll give us the ability to really not just, for example, measure what elements are in an exploding star, but measure how fast the gas is moving in different parts of the explosion, using Doppler shift measurements and so on. And so there's a lot of advances that we know how to build if you'll just, if you've got $1 billion or so, you can shell over for us. And so we're putting that in competition with some other really cool projects like LUVOIR that NASA's going to be reviewing in the next few years to decide what big mission they're going to be building for the 2030s.
Okay, so this is long-term strategic planning. What kind of assets do we need? I love the 256 color era. It brings me back to having a Commodore 64 in the 80s.
Right, exactly. So you understand why we want more, right?
Right.
It's still a lot more than we ever had before in X-rays, right? And so, but we need more. So. Chandra's done fantastic science. It's going to do more fantastic science, but we're ready now to take the next step. And we've been ready for a while. And unfortunately, because other missions have sort of soaked up the budget, with overruns and so on, there hasn't been an opportunity to have a replacement for Chandra. And so really we're trying to nurse the spacecraft along to not die, because right by now we should have had a Chandra 2 up, and we don't.
Because it's so expensive.
Because it's moderately expensive, yeah. A billion here, a billion there, as they say. Pretty soon you're talking about real money, right?
Right.
But that's the old Washington joke. It's not as expensive as a lot of the flagship missions that are being considered now.
Yeah, and I remember Carl Sagan way back saying, hey, if we would just get rid of one destroyer in the United States Navy, we'd be able to fund a ridiculous number of NASA missions. So let's see. With the X-ray telescope, we're still seeing through time. That imagery is being soaked up by a sensor, like a regular camera, but then it's being interpreted by a computer as to a possible range of colors. Is that right? Right.
Well, that's what you do in visible light cameras now, right? That's what your cell phone does. It's light travels at the speed of light. It hits your sensor. It gets recorded digitally, and then it gets turned into like a JPEG or something, right? And the computer displays it for you, maps those numbers to colors. And so the trick is that instead of mapping the number to the actual color, which we can't do because it wouldn't be very good for you. If I showed you an X-ray picture it would just look black to you, and you'd get cancer.
Hmm.
So instead, we
No, thumbs down.
So instead, we shift the X-ray colors down in software to be visible colors so that we can see them. And the way I think of it is, so you know that color in light, right, is like pitch in music. Blue is a high-pitched color, and red is a low-pitched color. And so X-rays are like super, super high-pitched. They're many octaves up the scale beyond what we can see here, right? And so I think of representing our X-ray data in visible light as playing the same tune, but in the key of visible.
Okay. All right. And I have not studied X-ray travel speed at all. Is it
well, X-rays are
faster?
Just
yeah.
And so they travel at the speed of light.
Speed of light. Same thing. Okay. Good.
Yeah, they're just the same thing. They're just a different, and you know, radio waves are light too, right? They're a very low frequency color. And so if you were to take your radio dial and tune, well, okay, you just use Spotify now, but if you still had an old transistor radio with a dial, and you like turn the dial from 90.9 NPR up through different frequencies, right? When you got to about 90 million.9, you would actually be tuning in visible light, and when you got to 90 billion.9, you would be tuning in X-ray light. And so it's just different colors of light, and we think of them as different things for two reasons. One, because we can't see outside this very narrow band.
Right.
Two, because you need different technologies to capture the different kinds of light. But the light itself it's just all the same stuff. It's just a big question of how much you stretch it, what its wavelength is.
Right. That would be a great explanation for the novices who run into here. Okay. Let's move on to, I remember reading in I think it was maybe the Wikipedia article on you, early in your scientific and educational career, you went through this experience where you were interested in studying something that you couldn't quite measure, and then it turned out to not be the way you thought it was, and you thought, okay, that's it. I'm going to do not an about face here, but I'm going to change direction a little bit and rely on and explore things that I can actually measure. And yet dark matter has been a major focus of yours through the years. And so I'm like, okay, well, how do these reconcile, right? How do you measure dark matter, and what have you learned about it?
Yeah, by theoretical astrophysicist standards, dark matter is like absolutely solid, and
okay.
You can absolutely measure it. You see the effect it has on the things around it, and so we can see we have sophisticated techniques now to measure how the invisible matter bends the light, for example, of things behind it. So we can measure how much is there, and we can see how things orbiting it are affected by it. So it's absolutely there, and you know, there are plenty of things like X-rays you can't see, right? But you know they're there, and so I think just the fact that it's invisible, and dark matter is really, you know, it's a misnomer. It's really transparent matter.
Okay.
It doesn't interact with light, but this transparent stuff, just because it's transparent doesn't mean it ain't there, and we can measure it. We can measure its effects. So, you know, in my early, so the quote you had was a little bit tongue-in-cheek. It was, you know, yeah. So for my thesis, I was working on hypothetical stars in the early universe that went bang long ago and might have made the sky glow in the present day, and things like that. And the question was, can you rule out the possibility that the universe is full of big black holes that were made by stars in the early universe that went bang very early on? And could that be the dark matter? And so, but you know, it's very hard to get a handle on that, because they're, you know, beyond where even our forthcoming telescopes can see, and plus they probably didn't exist. I mean, the result I got was that if they did exist, you would in fact be able to rule them out with these indirect arguments. So I thought, you know, we know I like black holes, but I have looked at a lot of dark matter, but really black holes have sort of been almost more the focus of my career. And so, you know, we know that black holes exist. There's one in the center of every galaxy, an enormous one, and there's bunches scattered around. And so, you know, maybe I'll study those in like more nearby. You know, only come into maybe looking at the universe 6 billion years ago instead of 11 billion years ago, and then, you know, that'd be a bit more parochial. And so I've dabbled a lot because I sort of have, I'm a bit ADD. I have astronomical deficit disorder. I can't focus on one subtopic for more than a few years. So I've played with asteroids, I've played with stars, I've played with galaxies.
All right. And so dark matter is a real thing. You can see its effects, and you've spent some time gathering data about it.
Yeah, and so most of my work that was directly on dark matter was a while ago, and it was more in terms of thinking about what effects it would have, and then going, okay, so you should go look over here.
Okay.
Or ruling out certain kinds of dark matter, because if you did that, for example, if you had too many big black holes in the galaxy, they would be accreting matter, and you would see them in certain wavelengths, and so that sets a limit to how many black holes, or big black holes around there can be. And so you can say, okay, so that ain't the dark matter, because they may be there, but there are not enough of them. And so arguments like that are, and these sort of what we call in astronomy upper limits, results of like, okay, we had a crazy idea, but it can't be that, is actually a surprisingly large fraction of astronomy. It's like ruling out, you know, loads of different crazy ideas to focus in on the ones that turn out not to be crazy after all.
That makes sense. Yeah, by ruling this out, we get part of the shape of the box.
Yeah, so because you rule something out, it doesn't mean that your paper is a failure. It's actually a contribution, because I like to think, because you've like, okay, we don't have to bother going down that route again.
Right. Okay. Well, let's move on to quasars then. That's been a topic that you've studied as well for quite some time. And I'm curious now, what can you say that's true about quasars, and what does the public need to know about them?
Right. Well, what's true about quasars is that they're much more important in the history of the universe than we realized 20 years ago. And so what a quasar is, it's actually when you have a big black hole in the middle of a galaxy that is swallowing matter. And of course, once the matter falls into a black hole, you can't see it, famously, right? It's black. But on the way in, the gravity of the black hole is like ripping this matter apart. And it generates a lot of energy. The matter gets really hot, puts out all kinds of light, including, not parenthetically, X-rays, and so you can see it from a really long way away. In particular, the amount of radiation. So we're familiar with nuclear fusion. The sun shines by nuclear fusion. Over 10 billion years, the sun converts 0.1% of its mass into energy by the one equation everyone knows, E equals mc squared. Right? It says mass gets converted into a little bit of mass, creates a huge amount of energy. So the sun, a tiny part of the sun gets converted into energy over 10 billion years. And the Earth intercepts a tiny part of that, and that's all the energy pretty much that we get on Earth. So it's an amazing amount. But a quasar doesn't just convert 0.1% of the mass of the sun into energy. It over 10 billion years, it converts 100% of the mass of the sun into energy every year. And so it is just enormously more energy than a star. And that's why you can see it a long way away. And so it turns out that this squeezing of matter as it falls in a gravitational field is actually a more efficient way of converting mass to energy than nuclear fusion. Nuclear fusion, you get about, percent out. It's a 1%. You throw in 10 tons, and a tenth of a ton gets turned into energy. With the quasar, you throw in 10 tons, and 5 tons of it gets converted into energy, and only 5 tons makes it down into the black hole. and so it's a hugely efficient way of turning gravity into energy, turning gravity into light, essentially. And so one weird thing about the black hole is, so your listeners may be familiar with the idea of falling into a black hole and getting spaghettified.
Stretched.
The technical term, spaghettification. And the reason for that is, if you have a black hole, if you turn the sun into a black hole, if you squeeze it down, so you had a black hole the mass of the sun, it ends up being about a mile across. And the gravity is super strong at the edge of the black hole. You squeeze all the sun down into a million mile across star down into a mile across. But more importantly, the gravity is changing really rapidly. It's dropping off really fast. And so as you fall towards the black hole, say you're falling feet first, pretty soon, well before you get to the black hole, your feet are traveling 1,000 miles an hour faster than your head, which will not be good for you. All right, so that's what stretches you out, because there's more gravity at your feet. The gravity is noticeably changing between your head and your feet. Now, with the big black holes, what we call supermassive black holes, so the little black holes, like, only the mass of the sun, are like scattered around our galaxy. They're the endpoints of stars, of big stars. But the supermassive black holes, there's like one per galaxy, caveat usually, and they're, instead of being the mass of our sun, they're 1 million to 1 billion times the mass of our sun, and they're correspondingly bigger. The event horizon of the black hole, the size of the black hole, instead of being a mile across, is the size of the Earth's orbit around the sun, like 100 million miles across. But what that means is that the gravity isn't changing so quickly. It just scales up. And so the gravity, you don't get spaghettified until you're already well within the black hole event horizon, and it's way too late to write home. And so you can actually survive falling through the event horizon and experiencing it. And so that's the cool thing about supermassive black holes, is you could get quite close to them without dying. But then after a certain point, you're through the event horizon and you're going to die, because it'll take you a few hours to hit the center. But the thing about a black hole, so the other thing you want to know about black holes, quasars are basically black holes with a lot of bad stuff happening around them, right? As you go into the black hole, the geometry changes. Euclid no longer applies. Left and right start going behind you. The amount of direction into the black hole becomes more than the amount of directions out, until you pass through the horizon. Every which way you turn is in. And that's why you can't get out of the black hole, is that there is no way out, literally. And it's actually literally in the math that space becomes like time. The normal difference between space and time is, in space, I can go forward, I can go back. In time, I can get to tomorrow, but I can't get to yesterday, sadly. And so absent a TARDIS, I'm stuck in that one direction in time. And the inside of a black hole is exactly that, mathematically. It's that your direction into the black hole has become the future. And so there's a bunch of other cool things about that, but it doesn't matter, because if you get into the black hole, you're not coming out. So you can't test that. But outside the black hole, you can get back, light can get out. And so we can study the regions near the black hole in actually quite some detail. And so that's what we do. That's why we're interested in quasars, because it tests the laws of physics, which are the rules of the game that we live by every day on this world. And it kind of tests them to breaking point, right? It puts them in a really extreme situation, and we can watch nature do that experiment and get a better understanding of the laws of physics.
Okay. Is there any interest in looking into that more efficient method of transferring matter into energy as something we could reproduce?
Yeah, the only snag with it is it requires a
black hole generator,
and preferably billions of times the mass of the sun. So it's not something you really have in your living room. So I don't see any way that that can be parlayed into something for use on Earth.
Right, or even in the galaxy somewhere. right?
Yeah,
Just
I mean, a
doesn't,
super advanced civilization
yeah.
might be playing with stars and smashing them together or something to do this. Yes, that you could imagine that. I think we're ways off. I wouldn't
Quite a ways, yeah.
just yet.
Right. Let's get good at leaving the solar system first.
Yeah, right.
Traveling around with it.
Yeah, this is something where the environmental impact assessment for a machine that can destroy whole galaxies is like not in my backyard. Thank you.
Right. Do it over there. All right. Hey, this is Jason Canigan, the host of the Cold Star Project and the founder of Cold Star Technologies. I've decided to do something new. I've started doing daily update videos on who I met and what I learned the previous day in the space field. And it's a great sort of follow me thing. You can learn what I learn. I'm meeting a heck of a lot of people and learning a lot of things really fast. And the space field is really disparate. There are tons of nooks and crannies to go into and explore, from legal, operational, regulatory, compliance, and gosh, the end customer. Who'd have thought about that, right? So you can sign up for this. If you go to coldstartech.com/MSB, that's short for Make Space Boring, the mission we're on, then you can sign up, and in your email you will get a daily notification that the new video has been posted. I'm also thinking about doing some branded mini courses and summarizing papers as I'm able to. So those will be some goodies that are in there as well. So if you're interested in that, go to coldstartech.com/MSB and join us on the mission to make space boring. Now back to the interview. Well, let's come back then to from those grandiose ideas to something simple, the International Space Station. It's being considered for commercial ventures. You've had some ideas to talk about that. What's your opinion on that? Can the ISS even physically handle this kind of change?
Oh, I mean, physically, yes. You could, if you had the money, you could do some useful commercial stuff on the ISS. What I don't see any way you can make a profit doing it. Right? I mean, the ISS is incredibly expensive to run, and the commercial experiments that are being done today on the ISS are getting a lot of that benefit for free. They're not being charged for the cargo ships, the astronauts, the maintenance, and all of that. And so I think if NASA, and so the problem is this, that we have the ISS, but NASA wants to spend its budget on moon missions. And if it's going to spend its budget on moon missions, it can't afford to keep running the ISS. And so it's desperately looking for someone else to pay for it. But I just don't see it. I mean, I think the amount of money that it would take to operate the ISS commercially is just insane from a commercial point of view. And the profits you could imagine making from microgravity experiments don't come within orders of magnitude of justifying that. Now, that's not to say that one couldn't have a profitable LEO space station for commercial purposes if you architected it differently. But it would have to be a lot more bare bones, designed with cost efficiency in mind from day one. It's not clear yet if that'll happen, but that's more likely than having the ISS be self-sustaining commercial.
That's kind of a shame. And it really does make you wonder what's going to happen if the moon missions do go ahead, because I think they can't do both.
I don't, so well, unless again you kind of cut back the defense budget by 1% and increase NASA's budget by a huge factor. So double NASA's budget and you can do it. But otherwise, I think that ultimately some administration will have to bite the bullet and go, ISS is going in the ocean. And it may even not be up to them. Maybe because the Russians have the rocket engine, so that's the other issue with his commercialization thing. That it's an international space station, and so the U.S. can't actually decide unilaterally. Right. They can decide unilaterally that on the U.S. segment they're going to do commercial stuff, and can rent it out. But they can't make sort of decisions about what orbit it's going to be in or without international cooperation. And at some point, Russia or Europe or Japan are going to have one of the international partners meetings where they say, no, I'm sorry, we're done. it's time to retire the ISS. And so it's not entirely up to you guys.
Okay, more more hands in making that decision. All right. If folks, if you want data about space launches, Jonathan's space page is the place to go, and that report. I followed you on Twitter for a while, and you pay a lot of attention to these launches. You're tweeting live updates. There's a lot of numbers and commentary on that, which I'm sure people appreciate. How much time does keeping track of and updating all that info take, like every month?
Yeah, I mean, it's hard to estimate. A lot of it is I've gotten very efficient at it because I've been doing it for 40 years, one way or another, and so I have a lot of background knowledge, which lets me not have to waste a lot of time figuring what's going on here.
Right.
And a lot of software that I use to analyze the orbits and things like that. So it's something that I do when I get home from work for an hour in the evening to wind down, right? And so it's nice because it doesn't have deadlines associated with it. No one's marking me, kind of thing. So it's sort of, it lets my whizzing brain, just sort of slow down eventually in a relaxed way. And so it's so I spend probably an hour a day in the evening, and then some time at weekends working on it. And it's been I did it because I wanted to know this information. Right. And I started sharing it, as we were getting a lot of space inquiries at the observatory from the public that is not really something that we do. And so the public affairs people kept asking me, and to sort of fend them off, I started making this report to go, okay, everything you're going to need to know about this week that you'll get phone calls about is in this report. And someone suggested, well, maybe, one or two other people will be interested in this, and you should put it on the internet, and maybe 3 people in the world will want to read it or something, but it turns out that several thousand people subscribe by email. I've got 30,000 people following me on Twitter. So apparently there's an appetite out there for geeky level detail about our exploration of space. But that's not what motivates me. What motivates me is the historian 500 years from now who wants to know what exactly happened in those pioneering early days of humanity's steps into space. And I was frustrated because in the official histories of like NASA projects and so on, there's a lot of information about the politics of funding it and the design before launch, but they tended to do a very poor job of actually saying what actually happened once the damn thing got off the pad. And that's mostly because professional historians are trained to care about the people and not about the hardware. And I think what the hardware does is interesting because that's kind of the whole point of why you were doing it. And so I set myself up with the job of being the journal of record for what actually happened to the missions once they got launched.
Okay. And I found that very amusing. I mean, you've got a giant reason why to be doing this, but it's, for other people looking in on that, oh my gosh, it's such a huge project in an hour a day, and it's like an exercise commitment or something, and for you, well, Jonathan's relaxing doing this, actually. Pretty funny difference in perspective there.
This or a NASA management meeting, no competition.
Right. Okay. Well, and I'm curious, what kind of connections and opportunities have come your way over the years because you've had this asset that you've been working on over here? Yeah,
there've been a few. I mean, to say, for me, the interest in getting connections and opportunities more to get more data for the report, rather than for anything for me. But I've gotten to meet a bunch of senior space program people. And I've gotten, sort of insider view of some of these things. And I did get one nice junket. Arianespace very kindly gave me a seat on their plane to one of their launches in Kourou. So that was an experience I'll never forget. And definitely made me want to I was already covering the Ariane stuff in detail. This is the French, well, European rocket provider. And so they have this fantastic base in the Amazon jungle, essentially. Except it's on the beach. Imagine you have a Caribbean beach, the Amazon jungle, and 100 yards strip of France separating them. And that's French Guiana. And so, you go into Kourou town, and they have the boulangerie and the patisserie and all the sort of the Renault car dealership and all this stuff. It's very French. And, but it's in this incredible jungle beach, South American environment. And then you have rockets and launch pads and stuff, which is cool. And the French Foreign Legion guarding them. And so that was my number one most amazing opportunity that came out of it.
Very cool. Very cool. I'm originally Canadian, so all those words made sense to me. So that was fun. That is a surprise connection. You can't afford to be second best. You need to be first, and that requires speed. Now, if you're thinking that growth is supposed to be slow and steady, frankly, the way I was taught back in the 90s in the operations management and business administration programs, you are too slow. We have to adapt. And in space, it's no different than anywhere else. People like to think they're special in space, and it is fun, all the stuff we get to work on, but business is business. The fundamentals nowadays are conservative growth is not good. You need to run as fast as you can and risk outstripping your supply lines, which means in our world, using up the capital that we've got. That's a risk. But there is no prize for second place. There certainly is no prize for third. If you want to scale operationally fast, come talk to us at Cold Star Tech. We are the process experts for scaling fast. Now back to the interview. Okay, let's finish up talking about mega constellations and small sats. There's a comment in the Wikipedia article on you. McDowell has long campaigned for U.S. compliance with the UN Convention on Registration of Outer Space Objects, 1975, and UN Resolution 1721B, 1961, which of course I went and looked up, and they linked to commentary that you had. But this was about 20 years ago, and of course the Wikipedia article talks about it like it was yesterday, right?
Well, I'm still campaigning about it.
Yes. Okay.
And in fact, I made a stink about the fact that earlier this year the U.S. announced that they had deployed secretly some satellites from the X-37, which is blatantly against international law obligations that they have. They're meant to register them with the UN and stuff. So yeah, I believe strongly that transparency in space operations is actually beneficial to international security. And there's and I have this quaint belief, that the U.S. should actually obey international law once in a while, and take treaties seriously and things like that. I know it's unfashionable, but that's where I am. So I published a paper last year, which I call the Hall of Shame paper, in which I sort of listed the various satellites from various countries that have not been registered with the UN. So it's about 5 to 7% of all satellites never got registered for one reason or another. And often, surprisingly, it's like turf wars. It's like which country is actually responsible for this satellite? Because for example, the Hong Kong company, when Hong Kong went over from Britain to China, there was one in the middle that got missed before the registrations and stuff, or globalized companies where there's some discussion about whether this is really an American company or a British company, or so in among all that, there's the very occasional naughty activity of hiding a secret military satellite by not registering it, and that's why we have to keep the whole thing kind of more, clean up the whole thing so that people can't get away with that. That's my so as a result of so I started making. Let me wind back a bit. I started making a list of satellites. So when I was 12, I think, I came across James Orwell's aircraft. And in the back, it had a list of the satellites launched this year, which I meticulously copied out. And then pretty soon I realized that actually that list wasn't such a great list, that there were gaps in it, or it wasn't 100% right. And so I started off trying to make a better list, right? And so 40 years later, I have the best list, and so then that inadvertently, just this sort of librarian bookkeeping anal kind of drive to, I want to know what's in space, led me down this path to the policy side of things. Of, actually, there are good reasons of international peace and security why it's important to have such a list. And there are all kinds of policy implications. There's the let's not put nuclear weapons in space. There's the let's control space debris and not have it ruin everything for everybody else. All these different kinds of policy issues that come really pretty directly out of trying to figure out what there is in space. And so that has and there are a lot of people, so I've made friends with a bunch of space lawyers. And a lot of people are kind of surprised that there is such a thing as a space lawyer.
Yep. I'm doing the same thing.
Yeah. And, they range from everything from like the people who, if you have a communication satellite that you want to sell to some other company, all right, that's going to need lawyers. So that sort of everyday lawyering kind of stuff, up to the sort of more constitutional law, kind of international law kind of thing of what should the Outer Space Treaty say? How should we change it? So it's a vibrant field of law, but a lot of the people involved in it don't have a technical background, and so they love having someone they can call up and have do the orbit stuff for them, the technical stuff. So I've been doing quite a bit of that, and it's been a lot of fun, and gets me out of gets me hanging with a different crowd than I would normally hang with. So I feel good about that, but it really does come very directly. All these policy issues come directly out of just the geeky bookkeeping that I've been started off trying to do.
Yeah, very, very interesting. So the guys like Dr. Maria Bajaj, the space situational awareness guys, and the space lawyers like Christopher Johnson at the Secure World Foundation, both who I've interviewed on this show, and I have a number of other space lawyer interviews coming out. They all echo what you're saying, and the simple vision that people need to understand is satellites go up in similar orbits as these mega constellations, and if there are resident space objects up there that nobody knows about, something is going to crash into them, and that's going to create a problem. And that is the sort of thing wars get started over. So
that's exactly
better be clear.
Wars can get started over misunderstandings too, right? So having clarity is important. And so the thing to understand about space, what makes it different from sort of international activities elsewhere, is that if you're a satellite, you're traveling at 7 kilometers a second. So is that like 5 miles a second, something like that? And so several hundred miles a minute, right? You go around the world in an hour and a half. And so it's intrinsically good, and everyone's satellites is like crisscrossing and going everywhere, right? And so there's no American zone and Russian zone. Everyone's like mixed up, and things are happening very fast, and you're not over one country for more than a few minutes. And so trying to have, say, an American space law and a Russian space law just ain't going to cut it, because you're going to be switching jurisdictions too quickly to keep track. So space is intrinsically global in that sense, and we have to tackle it as an international community. And the other thing about space is it's hard to hide, because any decently sized satellite is visible in telescopes, and if it's in low orbit, it's visible to the naked eye. And so a lot of the secrecy, and particularly the US military community around space, is a little sad, really, because they're like, "Oh, we can't confirm if that satellite is up there," and I can see it.
I see an energy trail.
That bright thing going overhead. That's it. And so there's a sort of a mindset in certain areas that by stamping secret on something, you can actually make it secret, and you can't do that if everybody can actually see it. And so people have to just, I think people are starting to get over that now and realize, okay, yeah, we don't, it's not actually buying us anything to make these things secret. So we'll see. So I'm mildly optimistic about that side of it. I'm concerned about the space traffic management because these mega constellations are coming fast, right? And we're going to have many, many more satellites up there in the next few years, and the speed of regulatory change to keep up with that just ain't there. And so it's going to be a mess, folks, and I'm worried about that.
Yeah, human beings seem to have an accident in order to make change happen in a quick way, and that's personally what I predict here, and hopefully smarter heads will prevail in the meantime, but
yeah, not optimistic.
Yeah. Well, Dr. Jonathan McDowell, thanks for being our guest today. I'm going to post links to your website underneath there. And how else can people get a hold of you if they're like, hey, I want to find out more or talk to you? What's the best way?
Yeah, if you Google Jonathan and space, you'll find me, right? And so I'm out there on the internet. Talk to me on Twitter, Planet4589 on Twitter. And that's probably the easiest way to get me. I'm always happy to talk with fans of space.
Right. Very entertaining Twitter feed. Thanks for being here today.
All right. Cheers, Jason.
You bet.